Good morning, everyone. For those of you in Pacific time, thank you very much for joining this webinar. We hope everyone is staying safe in this unprecedented time of COVID. Anyways, we are absolutely thankful to have Dr. Todd Dickson from IBM in Yorktown, New York, join us to give this webinar. Before we get going, just wanted to just, like I say, wish everyone staying safe and well. We don't know how long it'll be before we'll be able to rehost our meetings back in the Qualcomm auditorium. It looks like it's probably going to be a little while, in the order of quarters, not months. And so until that time comes when it's safe for everyone to meet in a conference room or in a seminar room, we will continue to host these meetings remotely through this webinar format. Okay, so we have some speakers coming up. I believe we've got Mike Chen, who is talking on either the subject of digital DLLs or digital phase lock loops or SAR ADCs, and also we've got Professor Boris Berman from Stanford, who is talking about. I was going to be talking about analog circuits for machine learning processing or compute. Okay, so anyways, let's get to the main event because we've got plenty of things that we have in store. So we've got Dr. Todd Dickson from IBM TJ Watson presenting today on high-speed SerDes transmitters for very, very high speed. So let me just briefly go through Dr. Dickson's bio. So he received his bachelor's and master's from the University of Florida and his PhD from University of Toronto. He's been with IBM TJ Watson Research since 2006 and currently leads projects related to very power-efficient I/O solutions. Very, very distinguished in our society, in Solid-State Circuit Society. He's had many Best Paper awards, including JSSC Best Paper in 2009. He received the Best Paper award at CICC. He's very, very, a distinguished volunteer in our society, having been associated editor for Solid-State Circuit Letters at the moment. He's in the CICC Technical Program Committee. And most notably, we are very excited to have Dr. Dickson because he's currently a Solid-State Circuits Distinguished Lecturer. Okay, so without any further ado, Todd, please take it away.
All right, thanks, Alvin. It's a very kind introduction. I know that these are, obviously I work in research. Never really expected that part of the research would be researching the most effective way to do live webinars. But the good thing is that I can do it from my home. The bad thing is that I don't get to join you guys there in San Diego. So, as Alvin mentioned, the talk is on high-speed serial transmitters for PAM4 applications, 56 to 112 gigabit per second. Let me just make sure I can move my slides. So, as Alvin mentioned, this is a Solid-State Circuit Society Distinguished Lecture. So, because of that, there's a few boilerplate charts that I'm going to walk through. Just to sell you guys on the benefits of membership of the Solid-State Circuit Society. Just about there's lots of resources that are available, opportunities for networking like this event. Educational material that's available. Just highlight a few things on the Resource Center on the website that's given there. You can find lots of material that's free for Solid-State Circuit Society members, webinars, short courses and tutorials from previous conferences, lectures that are available. There's a Solid State Circuit Society YouTube channel that again has free educational content from Solid State Circuit Society conferences. From actually just looking at the slide here, there's one from Alvin from CICC, I think last year. I think most people are aware of the conferences that the society sponsors: Isscc, VLSI, CICC, Asian Solid State Circuits, and European Solid State Circuits. There's a discount registration fee for Solid State Circuit Society members. So far this year, both CICC and VLSI have been moved to a virtual format, and at least in my opinion, I feel that they went very successfully given the times that we're in. I'm not sure what's the status for Asian Solid State or European Solid State Circuit Society circuits conferences at this time. The society has many flagship publications like the Journal of Solid State Circuits. Solid State Circuits Letters is one that Alvin mentioned. I'm actually an associate editor for that. And there are some new open access journals that are available as well. So take a look at these on the Solid State Circuit Society webpage. And finally, there's lots of chapter-based conferences and workshops like the one that we're on right now. So with that, that's all the material I'll go through on the society. So one of the things that we talked about doing for this talk was to make it a little bit interactive and have some polls. I think Jeff's working on the polling. So hopefully there'll be a question up there shortly. So keep an eye out on the chat window and the polling for a relevant question for high-speed SerDes. But let me just start off with just an acknowledgement of this is not work that's done by me alone. The stuff that I'm going to present, there's contributions from many people at IBM Research, both in New York and in our Zurich Research Lab. Some of the work has been sponsored by what used to be the IBM SerDes team. It has changed hands in recent years from Global Foundries to Verisemi and now part of Marvell. And some of the material has also been supported by Department of Energy under Lawrence Livermore National Lab. So that's so those are the acknowledgments. So let's get to the fun stuff, which is the technical material. So just a quick outline for the talk. I'm going to start off, the first two bullet points here are sort of background material, the context of why we want high bandwidth serial communication, and just to give maybe some introductory material on high-speed transmitter concepts. Now, sometimes I give a similar talk like this at universities where people don't have any background on this material. My understanding is that there's a lot of people from industry on the call, which this stuff may be a little bit old hat to you. So you can mute me or go do other things if you find the introductory material a little bit too elementary. But then after we finish that up, we'll dive into just some design examples on some recently published PAM4 transmitters, one that I presented at Isscc back in 2017, and then 128 gigabit per second PAM4 that was presented by my colleague Zeynep Deniz at Isscc last year. And then I'll wrap up with some future directions and summary. All right, so let's start off just with the context. Why do we want high bandwidth serial communication? And really the application is, when we look at networking for data centers or to a lesser extent high performance computing. The compute layer, which can consist of many thousands of servers, needs high bandwidth access to the network through electrical interconnects from the server to the network access switch. And in order to scale these data centers, of course, we need to scale the compute capabilities without increasing the network diameter. this drives the need for having higher bandwidth switches to access the network. And so that's really the driving force behind a lot of what I'll discuss, at least in terms of pushing data rates higher. In recent years, 28 gigabit per second NRZ signaling, which I'll describe what these acronyms mean in a little bit, but 28 gigabit per second NRZ, 56 gigabit per second PAM4. These are what you'll find nowadays. 112 gigabit per second PAM4 is on the horizon. There's some standardization activity that's going on in the IEEE 802.3CK for that. And then looming in the distant horizon is what comes after 112 gigabit per second, to be 224 gig. And that one is a bigger question mark that maybe we'll touch on a little bit towards the end of the talk. But at any rate, all this stuff drives a need for higher bandwidth, mainly for higher bandwidth electrical interconnects, mainly for accessing the network. So OIF has been very active in developing the standards for 112 gigabit per second. There's a number of different ones that are listed here just to give a flavor of what the alphabet soup of standards acronyms or link definitions are. So from top to bottom on this chart, we go from extremely short interconnects, the MCM, something on a multi-chip module where we have transmission channels that are less than an inch in length, all the way up to the long reach, or the LR, where we can have distances that may be up to 40 inches or so with loss at the Nyquist rate of up to 40 dB. So because of the wide range of channel characteristics among these links, you'll find that that some of these, that there's not a one-size-fits-all SerDes solution for all of these. We can have very power-efficient links for communication on a multi-chip module, where the loss is very low. The standard doesn't call for any equalization or forward error correction, and as a result, we can have a very power-efficient PHY. As we push up to, of course, the long reach, where the losses are very high, the SerDes is expected to be much more complicated, with transmit and receive equalization, needs for very low jitter clocking, and particularly in PAM4 links, as mentioned in a little bit, the need for forward error correction to bring the bit error rate down from a raw bit error rate of around 10 to the minus 4 down to a target bit error rate of 10 to the minus 12. So that's just a quick overview of the space of links. Actually, just to, because these acronyms will come important as we go through the talk, but just the other ones, the MR is the medium reach, and then we get into the VSR, the very short reach, which is usually a chip to an optical module, XSR, which is the extremely short reach, and then MCM, sometimes this gets called a USR, or an ultra short reach. So, in these applications, how do we achieve higher speed links? Well, there's two ways that we can really do this, right? We can increase the number of lanes per port. Right? An example of this is 400 gigabit Ethernet, which can consist of 850 gigabit per second lanes. But usually, for power and cost reasons, it's desirable to scale the per lane data rate. For example, up to 100 gigabit per second is being standardized probably in the next year with as I mentioned before, the IEEE 802.3CK. So the key metric from the design of an ASIC, like a switch chip, is the bandwidth edge density, or the linear density, which is really just a question of how much bandwidth can we achieve off the given edge of a die. And this is limited by the term that I'll use colloquially is feeds and speeds. Feeds being how many lanes can we get into a chip, or how many channels can we get into a chip, and that's limited by things like packaging and pad density. there's a lot of interesting work that goes on in this space, but we won't cover that in this talk. Instead, in this talk, we're mostly going to be focused on speeds, which is really the per lane data rate, increasing the per lane data rate, which is again the focus of what I'll be talking about, at least on the transmit side. So when we think about speeds, one thing that comes to my mind actually is a movie from the 1980s, which actually took place primarily in the San Diego area. This was from Top Gun, where they had the famous scene where Tom Cruise's character, Maverick, and Goose, his co-pilot, are saying, "I feel the need for speed." And of course, what they were referring to in that movie, I think, it's been a while since I've seen it, but I'm pretty sure they were talking about the need for bandwidth for network access. I could be wrong. I may need to go back and rewatch that movie just to make sure. I think there's a sequel coming out too. So let's talk about speeds, and particularly how signaling is changing in these high-speed links. So for many generations, NRZ, non-return to zero, or two-level pulse amplitude modulation was the preferred choice of high-speed SerDes. In this, we send one bit of information per symbol, either a 1 or a 0. And this was the predominant choice of signaling due to its simplicity for most of the links up to around 32 gigabit per second. And that includes the 25 gig OIF standards and PCIe Gen 5. It has a higher SNR just because of there's if we think about the peak amplitude being constrained, there's a wide difference in the distinction between the 1 and the 0 levels. But at 56 gigabit per second, many standards, particularly for long reach, have moved over to PAM4. So PAM4 is 4-level pulse amplitude modulation, where we instead pack 2 bits into the same symbol width. As I mentioned, this is used for 50 and 100 gigabit per second standards, including 64 gigabit per second PCIe Gen 6. It makes better it's more spectrally efficient by putting basically 2 bits per symbol, so it has the same Nyquist rate as the same UI or unit interval as NRZ or PAM2, but it does come at the expense of an SNR penalty, just because of the fact that the difference between levels is now reduced. The spacing between levels is reduced by a factor of 3 as compared to NRZ. So this does drive up I/O architectural complexity, and many standards now call for, as I was alluding to earlier, requires some sort of forward error correction in order to achieve the target bit error rate. Now, in networking applications, this is less of a concern. Of course, when I think about FEC, I think about latency. That's going to add link latency. And in networking applications, that's usually less of a concern. In high-performance compute applications, that can be a little bit more of a burden to overcome. So, of course, as we transmit data across a wireline channel, we should really think about the channel as being a low-pass filter. It's a bandwidth-limited channel, and when we send data, either NRZ or PAM4 data, across this bandwidth-limited channel, a single bit pulse can get smeared out over multiple UI or multiple unit intervals, and as a result, we have intersymbol interference or interference from that bit, which interferes with the detection of subsequent bits, or in some cases in the previous bits. So we refer to these as basically post-cursor intersymbol interference, or ISI that occurs after the main bit, which interferes with subsequent bit detection, or precursor, basically ISI terms that would interfere with bits before that. This is not a non-causal system. You can just think about this as a finite rising edge and a finite falling edge. Of course, the idea with equalizers in a high-speed SerDes is to basically to remove the intersymbol interference such that we can have highly reliable detection of the data at the receiver. Of course, ISI from these bits results in a closed eye diagram like what's shown on the right here, and we would need equalization to detect the levels. So, in case you're unfamiliar with the concept of equalizers, maybe you've heard about it or you've seen this in the context of home theater signal processing, right? You have an equalizer. The idea of the equalizer is to, in a home theater application, is really to shape the frequency response such that the audio quality is beneficial for your ears. So it's a similar concept in wireline communication. Here we have transmit and receive equalization in a wireline communication system. And here, and I'll pause for the groans, is that here this is supposed to be for the benefit of your eyes. Now this is one of the downsides of a webinar, is that I can't see the look of disgust from the bad puns in my jokes with this one. But again, that's the basic idea. It's just a form of signal processing to make sure that the levels are easy to distinguish. All right, so let's just look at a quick high-level block diagram of a typical SerDes, both in the transmit and receive side. This is what I would refer to as a classic analog mixed signal I/O solution. In the transmitter consists of data that may be coming in from an ASIC or a processor, which gets serialized up. We apply some feed-forward equalization, or FFE, and I'll describe what this is in a little bit, along with some low jitter clocking that's required to have good low duty cycle distortion for the data that's being transmitted. This gets launched out through a driver, through a that's impedance matched to a 50 ohm single netted or 100 ohm differential channel. In the receiver, we then receive the data, usually with some sort of analog front end, which typically consists of a continuous time linear equalizer, a CTLE, or a variable gain amplifier, VGA, which basically just does some analog signal processing before we feed this into the sampling circuit. And then once it's sampled, once the data has been sampled, we then apply a decision feedback equalizer, which uses intersymbol interference from previously detected bits to remove ISI from the sampling of future bits. So this is the predominant architecture that was used for many generations. In today's, particularly for long reach applications, they've moved away from this and have switched over to DAC-based transmitters with ADC-based receivers, and that really aids in basically the idea there is to move all of the equalization into the digital domain so you can implement much more complicated equalizers than we have in the analog mixed signal domain. But at least these architectures are still very relevant for short reach links, as we'll talk about in a little bit. So that gives sort of a context of links. Let me just talk a couple of slides about some relevant concepts for high-speed transmitters before we dive into the transmit material. Once I finish up this section, I'll pause to take maybe a couple of questions before we move on. So let me first introduce the concept of a feed-forward equalizer. Again, this is for people who may not be familiar with this material. A feed-forward equalizer is just another word for an FIR filter, finite impulse response filter, which is used to compensate typically at least a portion of the channel loss. In the FIR filter, we take the incoming data, we delay it, and then we weight it with appropriate filter coefficients before summing this to send to the to send out, at least in the case of a transmitter, send out through the driver. So mathematically, we can write this expression x of t as a combination of delayed versions of the incoming data x weighted by the various coefficients, x of n being the main cursor, or basically the data that's being transmitted. We have then precursors and post-cursors as well. Precursors being ones before the main cursor, again, post-cursors after the main cursor. And the convention is that the number of caps in the FFE is just given by the number of precursors, the number of post-cursors, plus the main cursor that represents the number of caps in an FFE. So these are very common in serial transmitters, at least in the analog mixed signal implementation that I was just showing, mainly because of the fact that the delays are simpler to implement. I can implement these using just flip-flops or latches. Mathematically, you can do the same thing in the receiver, but the delays need to make sure that they preserve the data and the intersymbol interference, and so there's much more stringent linearity requirements on the delays if it gets implemented in the receiver. But for that reason, it's typically implemented in the transmitter. In the case of ADC-based links and DAC-based links, these are still done in the digital domain. The coefficients are digital, and then the output is then sent to a transmit DAC, for example, in the case of a DAC-based transmitter. Now, one thing to note with an FFE is that, since the transmitter is sort of peak amplitude constrained, really what's being done is that, like if I think about, for example, I want it to have higher amplitude for higher frequency content, like a 1010 pattern. So to achieve that, we're trading off or de-emphasizing the low frequency content, and that's typically what's done in an FFE, which means that usually that we need a VGA in the receiver to recover that amplitude that's been de-emphasized. So one other concept just to go over is the different types of drivers that are used in high-speed wireline links. Again, these are for electrical applications. Current mode drivers were basically like a CML type or current mode logic style driver, where based on the data, we just steer current into one of two differential outputs. And in the current mode logic, of course, the termination, the TX termination is achieved based on the load of this CML driver. On the other hand, the voltage mode driver has been used a lot recently. And in this case, really, I think of a voltage mode, sometimes it gets called a series source terminated or Sst driver. I think of this as really just a glorified CMOS inverter, right, where but of course, the part of the purpose of the CMOS inverter is to make sure that the transmitter is impedance matched to the channel characteristic impedance. So usually the termination impedance for a voltage mode driver is a combination of some linear resistance and an actual resistor plus the pull up or pull down impedance of the FETs that are switching. And to allow for tuning, impedance tuning of the Isscc to account for variability, for example, in the threshold voltage or the on resistance of the CMOS switch, a lot of times you'll see header and footer devices that are inserted in series with these PNN MOS to allow for impedance trimming. Now, one of the reasons the SST is widely used is that there's a theoretical advantage in terms of power efficiency. You can compute for a given amount of voltage swing the current that's required in the drivers, and you can show very easily that for the same peak-to-peak differential launch amplitude, the SST requires 4 times lower current. So this is a reason why they've been predominantly used, but I do want to make a point on that in that, in a lot of these links nowadays, the termination current is not really the dominant source of power consumption in the transmitter. Not to say that it's negligible, but in some of the examples that I'll show, it's like 15%, regardless of whether you use a voltage mode or a current mode driver. Another way to think about it from a power efficiency standpoint is that the termination current is fixed, and hence as I go higher and higher in data rate, the termination current becomes less in terms of picojoules per bit or milliwatts per gigabit per second, basically a measure of the efficiency of the link. So how do I turn this into a feed-forward equalizer with these two different driver topologies? Well, with an SST driver, I said that basically these are, an SST driver is basically a glorified CMOS inverter. And typically what we do is we would, you think about like the size of inverter that would be required to get a 50 ohm match. So it's a big device, and typically we would just think about chopping that up into smaller and smaller pieces and then dotting these inverters together. And then we can achieve the desired tap coefficients based on the number of segments that are pulling up versus the number of segments that are pulling down. And the effective pull up or pull down strength gives us the FFE tap weight. Now, in order to get finer and finer resolution in the FFE coefficients, that means that I need to slice and dice this inverter finer and finer and finer. And that has a big impact in terms of, for example, the output capacitance or the wiring from the output of this SST driver to basically connect all of them together. Now, in typical architectures, once we start to break these up, and this is something that's done in order to ease the delay requirements or the delay generation of the FIR filter to push that to lower speeds, we then push this at least a portion of the high-speed serialization into the segment with the SST driver. So as we start to slice and dice this SST driver finer and finer, we're also increasing the amount of parallelization of the, for example, the serializers that feed into the driver and so forth. Now, on the CML case, the story's a little bit different, right? In that basically, now my driver is not really a portion of the impedance match of the transmitter. Remember that that's done with the 50 ohm load resistance, for example. Right? So as long as I size my, sorry, can someone go on mute? As long as I size this CML, the CML driver to handle the maximum current, then I don't need to basically slice and dice this to achieve finer tap resolution. In fact, I can just control that externally or outside of the high-speed path using, for example, a current DAC, which can. Sorry.
Sir, can you please mute yourself if you are not asking a question? Thank you.
So the DAC.
Sir, can you please mute yourself if you're not dialed in or if you're not asking a question? Sir? Thank you. Sorry, Todd, please proceed. Sorry about that.
So we can basically control the tap weight. Basically, for example, we could use a high resolution IDAC that's outside of the high speed signal path to get finer and finer tap resolution in an FFE. Of course, this comes at the expense of maybe some additional area, but the key point is that it's outside of the high-speed path, and so it doesn't really impact things like output loading and so forth. Right. So the question really that I wanted to, by bringing this up, is to really pose the question as to, for an SST, even though the driver has a theoretical advantage in terms of power efficiency, as we slice and dice this to get really fine tap resolution, at what point does all the extra serializers and pre-drivers that are needed, does all the power consumption of that start to outweigh the theoretical advantage of a voltage mode driver in terms of its just termination current? So that's just a thought, maybe an open question for those of you that are working in this space. So with that, that brings me to the end of the first section. I don't know if we got a poll question or not, but I thought that we would stop and maybe field a couple of questions on some of this introductory material before we start to dive into the other high-speed design examples.
So, Todd, I apologize for the interruption. I don't think Jeff was able to get the polls to work this time, but we do have a couple of questions I want to just ask. So my question is related to the number of flops the staging flops that you use for the FFE or for the filter. So you're using essentially like an FIR filter, right? And as we're going to higher and higher data rates, obviously the UIs are getting shorter and shorter, and to equalize a certain channel impulse response or you need basically more taps, right? But historically, I've seen that really the number of taps in the transmitter FFE has not really increased much beyond, like, say, 4 taps. And so, is it because power that's limiting us from going to more taps? That's one question. And the follow-on question is, well, why not consider, for instance, IIR implementations for transmit equalization? You don't need to, if it's an IIR filter, you don't need to, like, increase the number of taps as your UI gets smaller and smaller.
All right, so let me address those one at a time. So first of all, let's just talk about the tap count. So that is probably one of the biggest disadvantages of the traditional sort of analog mixed signal approach of a high-speed transmitter. Right? Basically, if aside from the flops, the flops and the timing, that all gets handled at lower speeds, and then we kind of, I'll go through some examples on how we can get around this. We don't have any flops that are clocked at like 28 gigahertz. We deal with that at lower speeds in the architecture, and maybe use multiple phases of a lower speed clock to achieve that. But what does happen if I want to have like a 10 or 15 tap count FFE, then if I just look at this picture here, this is an old picture from a 10 gig transmitter did a while ago, but the idea still holds. So each of these triangles basically represents a CML output stage corresponding to different data delay and a tap in the FIR filter. And basically, if I wanted to, this would be for a 4-tap FFE. If I wanted to have a 10-tap FFE, I'd have to have 10 drivers dotted together in parallel. And that really then starts to load the output node a lot, particularly when you think about it like, if I think about like a tap that's way out, by like 10 UI after the main cursor, that tap weight is going to be considerably smaller than the tap weight of the first UI, right, or the first post cursor, right? So it's a little bit inefficient to do that in the analog domain, and oftentimes the trend now is to move to a DAC-based transmitter because it's much more efficient for a for a high-speed for a long tap count FFE. As I was saying in this chart, basically the only implementation difference is that this FIR and the coefficients, all of this gets done in the digital domain. Basically, in the analog domain, the summer is the driver itself, and we dot the driver to get all these drivers together to get an output waveform. In the digital domain, we do all of this in the digital. We have a digital, let's say in the case of a 7-bit DAC, we'd have a 7-bit output word that goes to a 7-bit DAC, and then the wave shaping is done via the DAC. Right? So it's true that for a lot of these higher speed, 56 gig, 112 gig, particularly for long reach applications where the tap count needs to be high, the trend, as I mentioned earlier, is to go to these these analog mix, these DAC and ADC based approaches. Now the other question about an IIR filter, that's an interesting one. I have seen some work on the transmitter to implement a sort of an IIR filter. I think I saw a paper on that probably several years ago now. I don't remember the details on it. One of the things that I mentioned with the transmitter, and one of the things we haven't gotten into in the talk, is how we adapt the equalizer, right? Because basically we need to know what is the ISI, and the only guy who sees that in the link is the receiver. The receiver at the sampling point, it's sampling data that has information about the data that was transmitted, but also all of the channel information, all the loss, the ISI information from the channel. So the receiver can do a great job of adapting itself. You can have some very complicated algorithms to perform, to determine the coefficients of the receiver equalization. The transmitter is a bit of a different story because the transmitter is just launching blindly into a channel. There needs to be some back channel adaptation. Basically, the receiver, this is all standardized in protocols for the receiver to send information back to the transmitter to say, hey, you need more precursor 1 tap weight, right? And while that can all be done, of course, it comes at the expense of latency. I can't update that tap coefficient very quickly. And so as a result of that, a lot of times the heavy-duty lifting, the heavy equalization is done in the receiver. A lot less is done in the transmitter, just because when you start to think about things like, voltage or temperature variations, it's a lot slower for that adaptation loop to compensate for it if that's being, if that's being implemented in the transmitter. So in a lot of these, even an ADC-based link, a lot of long tap count FFEs nowadays are being done in the receive side, after an ADC.
Got it. So just along the note of what you're saying, then the other thing I guess also to be concerned about is if you over equalize or put too much equalization on the transmitter side, I mean your crosstalk, your near end crosstalk, and is going to be a problem, right?
Yeah, I mean, anytime you basically boost up high frequency content right at the output of the transmitter, it is a concern. So, I mean, typically in these links, we don't rely on the transmitter alone to do the equalization. And in fact, as I was saying, a lot of it is done in the receive side, and I just sort of view that the transmitter in a lot of cases as just, hey, let's help it out a little bit to ease the requirements on the receive side, but you're not gonna be doing 20 dB worth of equalization in the transmitter.
Got it. So there's one question that came from online, and the question is, why do you use a non-causal FIR filter in the FFE?
So it's not non-causal. This is except I've had this question before. Maybe I didn't describe it. Obviously, non-causal, that would be very difficult to implement.
I mean, you basically have a bunch of staging flops, really, right?
Right. I mean, so
yeah, that was my thinking. Anyways, sorry.
I mean, you delay the data comes in, you delay it, and then look, I can call any one of these the main cursor, right? This is the main data bit that's being sent out, right? But it really just depends, which one's the main cursor versus the pre or post cursor. Really is a question of the tap weight as opposed to where it is in the delay chain, right? But the delays have all been implemented by some some shift register, and the system, of course, is causal.
Yeah. Okay. Thanks.
All right.
Do you want to continue with the part 2 of the presentation?
Yeah. Let's jump into that.
Yeah. Sorry. There's yeah, we can't get the poll working this time. Our apologies to everyone.
All right, so the next part, I'll talk about these two design examples, one on a 56 gig PAM4 transmitter that I worked really hard on several years ago, and now it's really just old news at this point because everybody's moved on to the 128 gig, 112, 128 gig stuff that's a lot more interesting. But it is, at least I think, maybe I'm just saying this because it was my design, but I think it's got an interesting approach that was used for delay generation, for high-speed delay generation for an FIR filter in the transmitter, which is then been applied to this this higher speed 128 gig transmitter that I'll talk about later. So let me just give a motivation for this work, aside from everything we've already talked about. The main thing in this 56 gig transmitter, the main difference between I think almost any other transmitter that you'll see, published transmitter that you'll see, is the use of what I would call a half baud spaced or T/2 spaced equalizer, right? So before I said that in this FIR filters we delay in increments of a unit interval, but there's some benefit to be had if we were to increment in half UI spaced or half baud spaced delays, right? In some ways, you can think about this as I decrease the delay in an FIR filter, I'm basically achieving a higher bandwidth filter, and that's sort of the thinking in terms of being beneficial for a high-speed transmitter. So we did some link level analysis. This was for something that I would call similar to a VSR link, a very short reach link, at least in terms of loss. It was a channel that had about 16 dB of loss at 14 gigahertz. We made some assumptions about transmit and receive responses, and how much equalization was provided by the receiver. The goal was to have a very power efficient VSR link. VSR, if you'll remember from the chart earlier, sort of like a middle of the range, not the long reach stuff. But this was the stuff, this was the space, at least at 56 gig, where it was a bit of a question, were people going to go with mixed signal approaches, analog mixed signal approach versus an ADC based. Anyway, what we found from these link level simulations was that we were seeing some improvement in terms of being able to pinch the ISI at the sampling point, which is a big deal for PAM4 because of the fact that, again, just because of its lower SNR, it's much more susceptible to what we call residual ISI or uncompensated ISI. And it also, because it's a higher bandwidth filter, has some improvements in terms of the horizontal margin as well. So based on this, we sort of decided we were going to go with looking into the implementation of a T/2 or half-baud spaced equalizer. By the way, earlier I had mentioned that for PAM4, it's sort of detrimental to high-performance computing links, or which are very sensitive to latency. There was another thing that at least early on we were thinking about with this, is that could we have an equalizer that may allow us to get a PAM4 link, at least for moderate loss, that maybe could avoid the use of FEC. Turns out that was a fool's game, and I don't think that anybody should think that the PAM4 can be done without FEC, but at least at the time that was sort of our thinking. So let's just talk about the high-level architecture of this test chip that we did. So it has a clock generation that takes a C1 clock and generates basically a full rate clock. This was external. There's no PLL on this test chip. And then generates the required subrate clocks, including quadrature clocks at the C2 rate. So this would be at 14 gigahertz, and at the C4 rate, or 7 gigahertz, that are then sent to these basically the SST segments. This architecture uses an SST style driver. There's lower speed serialization, which is basically just takes data from an on-chip pattern generator, serializes it, applies gray encoding that's needed for PAM4, and then we send that off to the transmitter. There's also some timing calibration that was done on this chip, but just in the interest of time, I won't go into details of that, but I'll refer you to the Isscc paper if you're interested in that. So on the clock generation side of things, as I said, we come in with a C1 clock, a full rate clock. We have a CML IQ divider to generate quadrature C2 phases. We convert that to CMOS levels using the CML to CMOS converter, and then we apply some duty cycle correction before we ship the C2 clock. We buffer the C2 clock and send it off to all of the SST segments. Then we take the quadrature C2 clocks, we further divide them. We have a dummy divider to balance the loading, and then we generate INQ C4 clocks, which are also sent to all of the SST segments, and then also lower speed clocks for the lower speed serializers. So the interesting stuff is in the segment itself. So before we go to that, the segments, you see that the data out of the serializer is broken up into MSB and LSB data for the PAM4 signaling. We then send this into segments. There's 17 MSB segments and 13 LSB segments. I know that seems like a little bit of an odd number. It just comes down to the tap resolution that was required and the maximum driver segment size that we would implement in the design. So here's the detail of the segments. Basically, we take quarter rate data in. We apply a sign bit, which just basically implements the polarity of the FFE tap for this particular segment. And then we multiplex the data up first through a 4:2 mux and a 2:1 mux. The 2:1 mux also performs the single-ended differential data conversion. And then we have a pre-driver and then an SST driver, which has some, as I mentioned before, some tune bits to tune the impedance. So this is a pretty standard SST segment, with the exception of these blocks down here, which are these phase selectors. Actually, before I get to that, so the lower speeds, sorry, the serializers and everything before the pre-driver operates on a 0.8 volt supply. The driver operates on a termination supply of 950 millivolts, and that's just to get higher launch amplitude, which is the thing that's important for PAM4 signaling. So the main thing that was different in this design was this use of these phase selectors in C4 and C2 for the C4 and C2 clocks. And basically, remember that we said that we ship quadrature clocks from the clock generation macro, both for C4 and C2. These phase selectors basically pick which phase we want to use for the C4 or C2 clock. And that's going to be done, and I'll go through a timing diagram briefly to show how this is done, but it's basically as a way to implement the FFE tap delays without using additional flip-flops or latches. Right? So the selector is pretty simple. It's just basically, you can think about it as just taking the I and Q clocks, XORing them with a sign bit, and then picking which of those that you want, and that then provides the clock phase. So we can get basically one of four clock phases coming out: I bar, Q, or Q bar. So here's just a quick timing diagram to show how we implement a half UI spaced FFE using C2 clock selection. So out of the 4:2 mux, we have this half rate data, right, that's launched on the rising edge of the C4I clock. And then we have these basically four clock phases to pick from on the C2 clock domain. So if we wanted to reconfigure this particular SST driver segment to operate as a main cursor tap, basically we were just going to take that half rate data and sample it on the rising edge of the C2IB clock phase, sort of in the middle of the half rate data I. Right? Now, if I want to then implement a precursor or post-cursor tap, all I need to do is just change my phase selection, basically a half a UI earlier for a precursor or a half a UI later for a post-cursor. And so just through clock phase selection, that then allows us the ability to implement the delays, basically to cause one segment to be delayed with respect to all the other segments just through clock phase selection. Right? And there's no flip-flops that are required. The only thing that's required is this pretty simple phase selection circuitry. Now, the similar technique can be applied for a UI-spaced FFE just through C4 clock phase selection. So again, here now we're going to change the clock phase that gets used in the 4:2 mux, basically to generate the half rate data. And in a similar fashion, if I want to configure a segment as a main cursor for a UI-spaced FFE, I'm going to sample that data on the rising edge of the C4IB clock, right, relative, so basically in the middle of the 4UIY data that comes in. Right? And then the 2:1 mux is then going to sample the half rate data on the rising edge of C2IB. If I want to implement a 1 UI delay, then in the 4:2 mux, all I need to do is sample this incoming quarter rate data 1 UI early or 1 UI late, and that's going to delay the data coming out of the 4:2 serializer. And then I also have to realize that when I do that, now I've degraded the timing margin on the 2:1 mux, which basically means that if I configure this for a 1 UI space pre or post cursor, I also need to change the phase selection on the 2:1 mux to sample on the rising edge of C2I instead of C2IB. So again, the same idea, just squiggling the clock bases around, and then allows us to reconfigure the segment based on the desired tap coefficient. And again, the number of these that we connect in parallel, which ultimately determines the tap weight for the FFE. So we implemented this in a 14 nanometer FinFET CMOS technology. The transmitter is 200 micron by 175 microns, as shown here. That includes everything: the clock generation, the PRBS generator, some decap that was in white space. The real heart of this is the Sst Driver, which is sort of shown in the blow up here. So here's all of these 30 driver segments, the total height of around 77 microns. And each of these, if I were to zoom in on one SST segment, it's basically done in a very regular digital fashion, using custom high-speed digital standard cells that have a total height here of 2.3 micron per driver segment, and then that includes everything from the input capture latches, the phase selection for C2 and C4, and then the serializers, and then ultimately the SST output segment. So just to show some measured results, we looked at this on a wafer probe test site across a channel that has about 6 dB of loss. This includes the basically total of 48 inches of high-speed cabling and a 2.5-inch trace Meg6. So the whole thing is about 6 dB of loss. It's well short of a VSR, but we're only relying on the transmitter for equalization. There's no receiver in this experimental setup. So one thing we see is that, so first of all, just to demonstrate the benefit of this T/2 spaced FFE, well, we looked again using the same hardware, since it can be configured either as a baud spaced or half baud spaced FFE. We did a comparison for the same channel to look at the T spaced FFE and the T/2 spaced FFE. This is at 45 gigabit per second PAM4 for PRBS 31 data, and you can clearly see, and this is one where you can see visually that you have much wider horizontal time eye openings with the T/2 spaced equalizer. Again, just due to the higher bandwidth. There's a modest improvement in the residual ISI, about a dB, which is about 10% or so. So it's kind of hard to really see that benefit with the naked eye. The one thing that I will mention and sort of stand out from these eye diagrams is that to equalize using a T/2 spaced FFE, as I go to a higher bandwidth filter, I typically need higher filter coefficients to achieve the equalization that's required, and that has implications, sort of as I mentioned earlier, on the output amplitude, or the amplitude that you get on the far side of the channel, basically the receiver input. So switching to a T/2 spaced FFE would require higher VGA gain in the receiver. At 56 gigabit per second, the results are not as pronounced, but there is some modest improvement in terms of the horizontal and vertical openings with the T/2 spaced equalizer. One of the limitations of this had to do with the granularity with which I can adjust the taps. I felt that I would have done better with this with higher granularity in the tap coefficients, which would basically require more tap segments, which is sort of a nice lead into the next work that I'll talk about on a high granularity FFE that's used for 112 gig applications. But just to summarize, this part of the work, here's the power breakdown both in the T/2 and T space mode. You can see that the T/2, trying to see, I mean, the powers are pretty comparable. There's not a whole lot of difference. The one thing actually that I do want to mention with this, and I sort of alluded to this earlier, is that the power from the driver itself. Right, here's the Sst driver, 15 milliwatts out of 100 milliwatts total, so about 15% of the overall transmitter. So, when we talk about the benefit of lower termination current, it's not as heavy hitter of a lifter, in terms of power as a lot of the serialization is, for example, the high-speed serialization. Here's the obligatory Isscc comparison table. I won't go through this. I haven't updated this since I presented this at Isscc a few years ago. But at the time, it was a very competitive 56 gig transmitter. All right, the power efficiency here is, 100 milliwatts or about 1.8, 1.7 picojoules per bit. So let's switch gears and we'll talk about this, probably the one that's more interesting, this 128 gig transmitter. This was the one done by my colleague Zainab Denez. So this is a 64 gigabaud, so 128 gigabit per second PAM4 transmitter. The high-level architecture looks very similar to what I just showed for the 56 gig. And we have clock generation. Here it's basically the same clock generation. I think it actually might be the exact same circuitry as was used in the 56 gig design. But now the input clock at 28 gig now represents a C2 clock or a half-rate clock at 28 gigahertz. The main point of interest for this work is these thermometer encoded slices, which are used to generate the PAM4 signal. So basically, out of this 64 to 4 serializer, we get quarter rate data that is thermometer encoded, and then we send that out to the driver segments. Right. So the real interesting work here is on the driver segment itself. So let me spend a little bit of time walking through the architecture of the driver. First of all, what we call the slice, the thermometer encoded slice, which is comprised of a number of different driver segments. There's 12 segments in total. And the main difference here is that we use a current mode driver as opposed to the voltage mode driver. I'll come back to that in a minute, but let's just walk from left to right on this to explain what all the blocks are. So first of all, we have the quarter rate data which comes in. We stagger it by one UI, which is just used in order to improve the timing margin going into the subsequent high-speed serialization circuit. So the quarter rate data basically gets ANDed with a one UI pulse that's done by ANDing together two phases of a C4 or a quarter rate clock, quarter rate quadrature clocks. Right? And that generates basically a one UI pulse of data, which is fed into an NMOS style MUX. So basically, this data feeds into NMOS pull down devices, and then there's a weak PFET pull up device in case none of the data are high. The output of this 4-to-1 MUX, and this 4-to-1 MUX also serves as a pre-driver. The output of this pre-driver then feeds into the driver circuit, and this uses what we refer to as a Tailless CML output driver stage. Classical CML, you typically need to keep both the current source and the switching differential pair in saturation. Here we only want to keep one device in saturation, which is the current source itself, which is this NMOS that's connected directly to the output node. So this is controlled by a bias voltage VSEG, and basically this acts as a current source. If the data is high, then this NMOS switch enables the current source. If the data coming in from the pre-driver is low, then this PMOS device basically pulls up the source node of this current source in order to cut it off. And of course, this is the half circuit. There's a complementary side which would be sending current out in that case. So that's the overall architecture. And of course, then afterwards, all the outputs from these current drivers get dotted together, and it goes into the ESD and T-coil and so forth. So let's talk about, because one of the benefits of this architecture is the ability to have very fine tap resolution in the FFE. So this is done sort of in two ways. First of all is the sort of the coarse tuning of the FFE tap weight is by reassigning the segment to a particular tap node, right? For example, to an FFE tap, so whether it's a main cursor where it's taking precursor or post-cursor data, right? And that's done through a C4 phase selection, similar to the mechanism that I talked about for the previous transmitter. Right? So that implements the coarse FFE tap weighting. The fine weighting, on the other hand, this is done through the bias voltage that's applied to the current source. Right? I mean, simple way to think about this is that I just have a fancy current mirror that generates the VGS of this current source, and then it sends out the appropriate current. And by tuning the VGS of this current source, I can then tune the current. And this is done through this is set through a DAC, as I'll show in a little bit. But as I'd mentioned much earlier in the talk, this is a benefit of CML is that, or current mode drivers in general, is that I can get finer resolution in the tap weight because I can tune this with maybe even a high resolution DAC that doesn't sit in the high speed signal path. So actually this slide shows the implementation of the biasing network to bias each of the segments. So basically we have, this is a 3-tap FFE. We have 3 different gate voltages that need to be adjusted, and these are adjusted through the fine adjust current DACs. I think this is a 6-bit DAC if I remember correctly. This then gets fed into a replica driver. Basically, as I was sort of mentioning earlier, this replica driver forms a current mirror with the actual output driver. There's some maybe some more circuitry that improves the performance of this. Basically, from a matching consideration, there's an op-amp circuit which basically makes sure that the drain voltage of this is equal to the lowest drain voltage from the driver in order to avoid, like, first order mismatch due to differences in VDSs. And then the switch network then determines which of these diode voltages or current source voltages are then being fed to the driver, to a particular driver segment based on how that driver has been configured for whichever FFE tap. So with this approach, we can get down to about 200 microvolt peak-to-peak differential tap resolution. Of course, that gets amplified by the number of taps that are being used to implement the number of segments N which are used for a particular tap. So it gives us a much finer control of the tap weight without exploding the number of driver segments that are required like you would in an SST. Right. So the phase selection is done a little bit differently than on the previous design. Right. We basically have pass gates which determine which of the quarter rate quadrature clocks are shipped through to this 1UI pulse generation. But the idea is still very similar to what we had in the previous design. Let's walk through a quick timing diagram. One difference is that the quarter rate data is, as I mentioned, staggered by 1 UI. Nominally, what we would want to do is we would want to sample just to get adequate timing margin for a really, really high-speed transmitter like this. What we would want to do is we would want to carve this 1 UI data on a third UI that the data is available. Right? And that, first of all, gives us adequate setup time margin. But the other thing is that then I have enough of a window to change the clocks, to reconfigure the clocks, to reconfigure this as a precursor or a postcursor. Right? So basically, this would be the main cursor timing. If I want to reconfigure a segment as a precursor, I just change the clock phases such that I sample 1 UI early on this 4 UI wide quarter rate data window. If I want to reconfigure it as a postcursor, I sample 1 UI later. So the design was implemented, again, this is in a 14 nanometer FinFET technology. The whole transmitter is about 294 microns tall by 165 microns wide, and that includes the T-coil and ESD that we didn't have in the 56 gig design. It's designed to tolerate the 1 kVm human body model and 250 volt CDM protection. I mean, actually, we have and I'll show some results on this, but we did this with and without the T-coil. One of the things that we find is we push up the data rate is just the challenge, not a surprise really, of how difficult it is to deal with the ESD capacitance, even with some bandwidth enhancement techniques like T-coils. So here's the measurement setup. Again, this was wafer probed. At these speeds, the setup is really, really tricky. We have to put the sampling heads for the scope directly on the probe card, and then make sure that nobody bumps the table to destroy, hundreds of thousands of dollars worth of equipment. So here's some measured results. This is at 64 gigabaud, both for NRZ and PAM4. We did this with the test site with the ESD and also without the ESD. The test site with the ESD has about close to 2 dB higher loss, which we measured based on the step response of the output of the transmitter. And 2 dB doesn't sound like a lot, but at these speeds and for PAM4, it really is a killer. So you can see that with this ESD, there's a lot lower eye opening after the equalization is applied at the output of the transmitter. But this is done with a 1 volt peak-to-peak differential launch amplitude. The power efficiency for PAM4 is about 1.3 picojoules per bit. Actually, one note on the launch amplitude is that this is one real winner of a CML topology, is that I can get higher launch amplitudes. I do have to pay for it in terms of a separate termination supply to accommodate the larger launch amplitude. Just allow me a minute and go back to the topology. We use a higher supply at the output of the transmitter than everything else. Right? And that allows for higher launch amplitude. This is something that you can't do in an SST because then you start to run into voltage rating issues with the devices. So it's another benefit of CML. So here's a power breakdown. The whole thing again is around 170 milliwatts. Again, which is 1.3 picojoules per bit for PAM4 data. Again, one thing that I'll hammer home is that the driver is not a huge portion of this. It's about 15%. All of the power is really, really spent in the high-speed serialization. Here, the final leg of the serialization, the 1 UI carver, the phase selection, and this 4-to-1 mux, which accounts for about 55% of the overall transmit power. And again, a comparison table. This one hasn't been updated for this year's Isscc, but it's still a very power efficient for this speed of transmitter. Actually, one thing we did was look at lower launch amplitudes at 112 gigabit per second to be able to get the power efficiency down to around a picojoule per bit. So I think that wraps up the portion on the design stuff. We have Alvin, do we want to take a pause?
Sure. There are a couple of questions, but just a time check. I mean, we've got another 12 more minutes before the end of the webinar time, but let me just ask a couple of quick questions. Is there a common tail current source between the out P and out N half circuits?
You go back. Say that one more time.
Okay. Is there a common tail current source between out P and out N half circuits?
No, there is not. So this is what we refer to as a tailless CML. So there is no tail device. This is the actual current source itself. And then instead of having like a differential pair on top that needs to be to switch based on the data, we're basically putting a switch at the bottom to enable that. And one of the reasons why we do that is because typically in a traditional CML approach is that you want to keep both the differential pair at the top as well as the current source at the bottom. You want to keep them all in saturation, right? Okay. And that becomes harder and harder to do with even at the 1 volt power supply. Right.
Second question, if you measure the pre-driver power versus the number of SST slices, what does that look like? It'll be interesting to see what the pre-driver dynamic power looks like with increasing number of SST slices.
That's a good question. I don't know if I have a precise breakdown of that. I mean, we have it for the 128 gig design, where the 4-to-1 mux is merged with the pre-driver, and you can see that it's like 21% of the overall power. But that's not just the pre-driver itself, right? It also includes some 4-to-1 mux functionality. But this is for a different design. The question is probably related to the SST part, and I don't have an exact breakdown of how much that pre-driver is. But if I were to, let me just swing back several slides. It's really all of this power. This is the driver segment, excluding everything but the SST driver, because the SST driver is on a separate supply. Now, it also the pre-driver is on that same supply. So the question is, is the 15 milliwatts, does that include the, what fraction is the pre-driver? And I don't know that. But again, the bulk of the power is in this, is in all of this stuff. And if we're looking on ways to reduce power consumption, this is the part that we really want to focus on as opposed to the driver itself.
Okay, so Todd, in the interest of time, can you continue with the rest of your presentation? Sure.
Yeah. Let me. So let me just talk briefly about some future directions as we look beyond 128 gigabit per second, and I'll put a caveat out there by saying I don't know the answers to this. I think a lot of people don't know the answers to this one, but it's an interesting question. As we look at a road to 200 gigabit per second, how are we going to achieve 200 gigabit per second on a single lane? Right. PAM4 is some early indications sort of indicate that PAM4 is not going to cut it. We can go to a higher order modulation like PAM8, but that's going to come at an even worse SNR than PAM4. So, does that then mean that we need stronger error correction codes or even coded modulation to achieve this higher data rate? One interesting approach that people are starting to look into is the use of what we call multi-tone transmission, and this was an idea that was that had some interest with some publications in the 80s and 90s. This was a publication from Irving Collette in 1989 that first looked at this from a theoretical concept of basically using multiple tones to transmit QAM data across a single wireline channel, and shows that you can get, at least theoretically, you can get within 9 dB of the channel capacity. So for these reasons, it's starting to get some interest for 200 gigabit per second over a single lane. So multi-tone signaling, sometimes you could refer to as discrete multi-tone. It's not a new concept. It was done in digital subscriber loops back in the 90s. And the idea is to basically subdivide the channel into multiple orthogonal subcarriers. And then based on the SNR of a given subcarrier, we can allocate how many bits we put in each of these subcarriers. In 2012, Fujitsu had done a demo of 100 gigabit per second optical communication using this approach. And I'll refer you to some material from an Ethernet work group back in 2012. But they did a demo of this at 100 gig. So, there's some advantages and obviously some challenges with this discrete discrete multi-tone transmission. Right? It does, the idea is that we can optimally load the subcarrier in terms of number of bits to achieve a higher bandwidth efficiency. Things like, OFDM are well known to have lower sensitivity to jitter than things like PAM4 and certainly NRZ. So that's another advantage. You could say that the design is the design and implementation is somewhat simplistic, although it hasn't been done at these speeds for dense I/O applications. But since it's been used in ADSL, it's a very, it's a proven and well-studied approach. The channel equalization is simpler. You don't need long tap count FFEs or DFEs. Of course, it does have some challenges associated with it. One is the higher peak to average ratio of the signaling, which can be as high as like a 9 to 10 dB of peak to average ratio. But there's also a concern with the longer latency. Basically, the data has to come in. We have to map this to a constellation, perform a inverse or Fourier transforms or Fourier transforms to convert from frequency domain back to the time domain. There's a addition of a reduced payload because of the overhead of the cyclic prefix that's needed. And there's also just a concern with the backward compatibility with the current time domain approaches for NRZ and PAM. So that's one approach that's been interest for 200 gigabit per second. Another approach that's of interest is that's gaining traction is to this idea of system on package design, where on a single multi-chip module with high density interconnects, we can now perform heterogeneous integration where the compute power is done on certain chips, and then all of the communication power is then spent on in different chiplets. So all the functionality is built is subdivided into various chiplets, and this then raises the possibility of integrating small form factor optical modules to perform the functionality of a long reach communication off of the module. So the communication between let's say the processing chip and the optical module would be enabled by high density routing. So this would be like a USR channel, high density interconnects, low power because the reach is less than an inch. And then this optical module could do the heavy lifting to transmit over long distances, maybe even tens of meters or even kilometers. So one approach or one project that's working in this area, this is an ARPA-E funded project called the Motion Multi-Wavelength Optical Transceivers Integrated on Node, which is it's an ARPA-E funded project to develop these small form factor optical modules. The first pass demo of this has used 16 56 gigabit per second NRZ modules to get a total of over 800 gigabit per second bidirectional bandwidth. But the future vision of a project like this would be to enable 3.6 terabit per second bidirectional bandwidth through the use of 112 Gig Pam4 as well as wavelength division multiplexing to get more information across a single fiber. So this is sort of a future work, again, just to enable more communication off of a module. So to summarize the talk, I've kind of gone of an overview of state-of-the-art high-speed transmitters, which are now, exceeding 100 gigabit per second for electrical links. The PAM4 signaling, because of its reduced SNR, it really requires much more precise equalization, which leads us to thinking of things like, new equalizers, finer tap-spaced equalization, as well as ways to implement finer control of the FFE tap strength in order to do a better job of pinching the ISI. and you know, I've hammered home this point a few times in the talk, but you know, SST voltage mode drivers, those have been prevalent for a number of links at, you know, 56, I would say in the 28 gig to 56 gig range, but current moded drivers they still have some advantage and maybe making a bit of a comeback. And then in the last part of the talk, we looked at the uncertainty ahead in a road to 200 gigabit per second. More advanced modulation is certainly going to be needed than PAM4. Whether or not that's done in the frequency domain or not for long reach links is maybe an open question. And really embedded optics in the first level package could be an avenue for power efficient high density IO solutions. So with that, I'll stop and take a few questions.
Great. Hey, Todd, thanks very much for an awesome presentation. Couple questions, you know, in the interest of, I mean, it's already 11:30 Pacific time, so sorry, folks, for going a little over, but let's take a couple, let me ask you a couple of questions based on what was asked, and then we can go from there. First question, does distributed ESD help at these speeds?
You know, I don't know. It's an interesting question. I think that the thing that may I don't know if this is at least what I think of when I think of distributed ESD is basically having, you know, multiple ESD devices that are maybe connected through, you know, multiple inductors or T-coils or something like that. And if it's something different, then maybe we'd have to talk offline on that. But I would say that the thing that prevents that is just density and being able to integrate lots of coils to distribute that ESD capacitance. So, I mean, you know, people are very creative on how they can do really compact, you know, multi-metal spirals for very compact coils. But there's always a question with ESD with those types of things as to, like, you know, if you make a multi-metal coil that goes into, you know, multiple metal levels, it goes into lower metal levels, those things have a harder time of handling the current, and you know, then it can just that can be a problem because you melt your wires as you try to get to the ESD.
Got it. So here's another kind of let's finish off with a general question. How do you anticipate, you know, the techniques that you've shown, you've discussed here, to scale into the more advanced nodes?
That's a very broad question. So, I mean, you know, like a lot of these techniques, a lot of the architectures that I've shown, well, I've shown two architectures for transmitters, and one thing is that, you know, when you look at them, they're digitally heavy, right? I mean, so, you know, aside from like the output driver, everything is digital. Now, it's not, you know, like I'm not going to go take a, you know, a standard cell library and design these things. They're done with custom high-speed digital, what we call standard cells, but they're really custom digital cells. You know, so they're, from that perspective, they're very process scaling friendly as long as you can, you know, design a high-speed, you know, custom digital library to accommodate that. Now, the big challenge is with doing that, particularly as you push these data rates up and as you go into more advanced nodes like 7 nanometer and beyond, and Alvin, you'd probably be the one to talk about this more than me, but it's just, you know, your EM capabilities to handle the current in the crappy metallization that we have in 7 nanometer and beyond. That's really that's the key thing which makes it difficult to push these data rates up. Those wires are not wires; they're resistors, and you know, that's a big problem, and they can't handle much current. That's the big thing. The other thing that's a concern, particularly, and I've sort of, maybe you've gotten the feel from this talk that I'm a bit of an advocate for CML drivers, probably because I've been designing them for many, many years. But one big disadvantage of a CML driver, particularly when you go into FinFET nodes with 14 and 7, is the self-heating in them. An SST driver, the nice thing about that, you have a, if you'll recall, the SST driver basically has an inverter and then a resistor, right? And typically, the majority of the termination resistance is comprised in the actual physical resistor as opposed to the FET resistance. So that means that the voltage drop, the majority of the voltage drop is across the resistor and not across the FET. So the FET has a lower drain to source voltage, and it does a better job with self-heating because there's this lower power dissipation in the FET itself. Now, if you compare that with a current source, where you have, particularly if you're trying to get like 1 volt peak-to-peak differential output swing out of a CML driver, you've got a larger VDS on that transistor. Aside from the fact that it's conducting more current, which we talked about the theoretical difference in the current requirements, it's not so much the current that's the problem. You can break that up and have a device that's conducting smaller current, but it really comes down to the VDS of the transistor. That has a big impact on the overall self-heating, right? And that's one thing actually. If you go forward with like DAC-based approaches, and if you have modulation schemes that are not 50% switching activity, if they have high conductivity factors, you can really end up into a situation where you can have very, very high self-heating, which is a big problem for CML. So that's my 2 cents or 10 cents on really the challenges as you push this into more advanced nodes.
Yeah, that's great insight. Obviously, being more and more digital friendly is great for latest nodes, but the supply is scaling. There's a lot of pressure, especially moving into tighter fins, and also if nanosheets we get there soon enough to actually scale the supply voltages even more, giving us fewer tricks to build these circuits. Yeah. Okay. Well, we're out of time.